welcome to this channel Dr.ARM's Chemistry. Friends, we were discussing the term and term symbols, and today we will see the term symbols or free ion terms and energy states of atoms. So, last time we have seen what are the free ion terms and how to find out these free ion terms for various configurations, that is D1, D2, D3, etc. And we will summarize these free ion terms for various configurations. So we will see the configuration and we will show here free ion terms. Now we will have the example of d orbitals, in which the electron configuration ranges from d1 to d10. So we will show here this configuration as d1, then d2, d3, d4, d5, and now we will see here d6, d7, d8 and d9, and here it is d10. And we will have the free ions terms for this configuration as here for d1 or d9, d2 or d10. The configuration with free ion terms are same. That is why we have shown these two configurations in the same line. So for d1 and d9 we have the free ion terms 2d. Then for d2 and d8 we are having this singlet S, that is doublet D, singlet S, singlet D, singlet G, then triplet P and triplet F. Then for D3 and D7 we have this doublet D, then quartet P, quartet F, doublet P, doublet D, doublet F, doublet G and doublet H. Then for D4 and D7 we have quintet D, then singlet S, singlet D, singlet G, then the triplet P, triplet F, triplet triplet D, triplet F, triplet P, triplet G, triplet H, and singlet S, singlet D, singlet F, singlet G and singlet I. Then for D5 configuration, this is doublet D, then quartet P, quartet F, then doublet P, doublet D, then doublet F, doublet G, doublet H, then doublet S, doublet D, doublet F, doublet G, and doublet I. And for detailed configuration, there is singlet S, then we are having octet D, octet G, and sextate S. So these are various free ion terms observed for these type of configuration. For D1 and D9, these are the free ion terms. Similarly for D2 and D8, these are the free ion terms. So in this way we are having D3, D7, D4, D6 and D5, etc. Now here we have to remember that these states are shown here when for any type of transition for this D1 or D9 or D2, etc. When we are showing the microstates, we are showing variety of microstates for the electrons. Then we find number of such free ion terms for each electronic microstate, and by ignoring the not allowed states, we are choosing the states which are not repeated. Means many of the free ion term states are repeated in microstates of the electrons. Therefore, we have shown here only those states which are not repeated. So, how to find out the microstates? So that we will discuss here also. Now, last time we have seen how to calculate the free ion term for given electronic configuration, that is D1, D2, D3, etc. And this helps to understand comparative studies of octahedral versus the tetrahedral. Similarly, the low spin versus high spin and D9 configuration versus D10 minus DN. D9, DN configuration means any of these. DN configuration versus D10 minus N. So for all such configurations, the term symbols can be assigned as we have shown in the previous lectures. And now we will go to see the I will see the electronic arrangements of microstates. Electronic arrangements of microstates. So you will see here the example for P2 configuration. For P2 configuration, Here we should know that the p orbitals are degenerate and triply degenerate, which contains px, py and pz orbitals. So the electrons interact with each other and result in the formation of a ground state, that is lowest energy state, and one or more excited states of an atom or ion. In addition to this, the electrons influence each other when we show the distribution of electrons, and if there are electrons more than one, then they show the influence of one on the other because of the interactions or the magnetic field produced by these associated electrons. So the interactions are arising by coupling of the magnetic field produced by their spins. Means when we show the electrons in the atomic orbitals, the spins of the electrons produces magnetic field, and these magnetic fields are coupled with each other. Then by second way, by coupling of the fields produced by the orbital motion of electrons, that is orbital angular momentum. When several electrons occupy a subshell, the energy states obtained depend on the result of the orbital angular momentum. Number of each of the electrons, then this resultant of all the L and ML values is denoted by a new quantum number ML. So the orbital angular momentum quantum number of each electron is used here to produce, that is result, the new quantum number called ML. So this resultant of all the L or M values is denoted by ML, and it defines the energy states for the atom. So we can show these energy states in different ways. So first of all, we will see how this P2 configuration is shown for different states, microstates, and these microstates are calculated by using the formula, that is NCR, that is NCR. So here we have to take this is equal to n factorial upon r factorial into n minus r factorial. So here n is equal to 1. This is n is equal to number of electrons. The n is equal to number of orbitals, or here we will say twice or 2 into number of orbitals, and r is equal to number of electrons. For example, for this P2 configuration, we will have this, the orbitals are 3, so 3 into 2 means 6, and number of electrons are 2. So this will show us that is n is equal to 6, means factorial of 6 upon R means number of electrons, 2 factorial into this n minus R means 6 minus 2 factorial. So this is equal to we can have this 6 factorial upon 2 factorial into 6 minus 2 means 4 factorial. So we can solve this to get this 6 into 5 into 4 into 3 into 2 into 1 divided by this 2 factorial means 2 into 1 into this 4 factorial called so 4 into 3 into 2 into 1. So by cancelling these terms like this, so we will have this 6 into 5, that is 30 upon this 2 into 1 means 2. So this gives us 15. So this gives the number of microstates for a specific configuration. So this is these are the number of 15 number of microstates for P2 configuration. This is 30. This is 30. So in this way, we can have the electronic configurations. 15 means 15 microstates are possible for P2 configuration. So we can show these configurations. 15 configurations like this. So if we are having say Px, Py and Pz orbitals, then we can have the distribution of electrons in this way. The 3 electrons, so this is with plus 1, 0, minus 1, that is these are ML values. So we can have the configurations like this. Now we will show this here. So there are 2 electrons available. So we can have this configuration like this. So this is first microstate, then second microstate, then third microstate, then fourth microstate, then fifth microstate, then sixth microstate, then seventh microstate, then eighth microstate, then ninth microstate, then 10th microstate, then 11th microstate, then 12th microstate, then 13th microstate, then 14th microstate, and 15th microstate. So in this way, we can get the set of these 50 microstates. So when we get such type of configuration of microstates and using the S and L values, we can find which configuration is best or suitable for a given element, that is say P2. So this can be seen by using the different ML and L values or JJ values, in which we are choosing the electronic state in which the S value and L value is maximum. So we can choose the microstate having maximum value for S and L. So that will be best the configuration. So that will be seen later on when we use variety of examples. Now we will see the arrangements and how we get the term symbol or different configurations by using the L and S values, S and L values. Here we are representing arrows in the length. We are representing the electrons in the form of arrows having appropriate length, which is associated with the quantization of energy, or which represents the quantization of energy. So, for example, if we take the configuration that is like P2, then we can have the energy states. We will show here the energy states. Energy states. So if we consider here these L values as equal to 1, it is represented by the arrow, say of this specifically, and again L is equal to 1. Then when these electrons are having the energy equal, the electrons are having same energy, then we will show this so the resultant of this gives ml equal to, so this is the ml is this L plus this M, that is L plus L. So sum of these L's. So we will get here this 1 plus 1, that is equal to 2. So this 2 ml value represents, we know the relation, that is when the value of L is 0, 1, 2, 3, 4, 5, 6, etc. Then this symbol is it is for here S, P, D, F, G, H, I, J is omitted, so it will, if it is 7, it will be K. Then for this 2, you will find that it is P, or for 2 value it is D. So we will show that the term symbol is these two. So this is B state. The resultant shows the D state. When the vector quantities, that is the orbital moment of the electron is in the same direction, then when the direction of one of that electron is changed, then we have the diagram like this. Here L is equal to 1 and this L is also equal to 1, but this ML value, this ML so ML is equal to 1, so this value is 1 and therefore it is P state. P state. When this vector is again coming close to this, the direction changes. So we will get this vector, that is L is equal to 1, having this direction, and in opposite direction there is another L is equal to 1. So the resultant is equal, ML is equal to 1 minus 1, that is equal to 0, and therefore the term symbol or microstate, electronic state, is called S. So you can find this 0, here use S state. Now we will see another example. So this is, so we will see. So in this way we can also see in the same way for P3 configuration or the ML values. So for P3 configuration, the ML values are like this. Here L is equal to 1 and L is equal to 2, means the quantization of energy for one is say single unit and for second electron it is double. So we can show this is the quantization of energy, and so this is single, this is double in length. So the length shows that the quantization of energy is here as a single unit, here it is double. As a result, this is showing the resultant ML is equal to this 1 and 2. That is 2 plus 1 is equal to 3, and therefore the state is, for 3 it is F. The state is F state. When this direction is changing in this way, so when the direction is changing, so this is in double length, whereas single layer. Means this L is 1, this L is 2. So this ml is equal to 2, and therefore for 2 the state is D. This, when this arrow is again changing in opposite direction completely. So this is L is equal to 2, this L is equal to 1. So the resultant ml is equal to 2 minus 1. 2 minus 1, that is 1, and therefore the state corresponding to this ml is 1, that is P. So that is P state. Then when this L is equal to 1 and another L is equal to 2, that is L is equal to 2, the quantization of energy is length of the two arrows are the same, and therefore the resultant ml is equal to 2. This is 1 because the length is same, so this is 1 plus 1 which is equal to 2, and therefore for 2 it is D state. Then if the direction is changing, then we will have this L is equal to 1 with same length. This L is also equal to 1, and this is also equal to 1, that is ml is equal to 1. Therefore resultant ml is equal to 1, and for 1 the state is P. Therefore P state. Then when the directions of this L is equal to 1 and this L is equal to 1 is also opposite to each other, then the resultant ml is equal to 1 minus 1 is 0, and therefore the state corresponding to A0 is ml0 is S state. And when this L is equal to 0 and L is equal to 1, then the resultant ml is equal to 1, and 1 corresponds to the state P, therefore P state. So this is for the P3 configuration. Similarly, we can get the energy states for D2 configuration. We will see for D2 configuration. So the coupling of L values for d electrons follows the similar pattern, except that for a d electron the L value is 2. So the arrow's lengths are doubled. So L value for these d electrons is 2. So the length of the arrows is doubled. And because of this, for d electrons, L is equal to 2. Therefore, arrow length doubled. Arrow length doubled. So we will see that when L is equal to 2 and with L is equal to 2, so the arrow length is doubled like this. And for this, the resultant ML is equal to this 2 plus 2 equal to 4, and this 4 corresponds to G. Therefore, G state. 2 plus 2 means 4. Now, if the direction of this is changing, then we need this so this ML is equal to 3 and 3 corresponds to F. Therefore, F state, that is the resultant. This is the resultant. Then if the direction of this arrow is reversed completely, so you will find that this L is equal to 2 and this L, ML or L is equal to 2, and therefore the resultant means this is again reducer here. L is equal to 2. So this resultant ML is equal to same 2, and for this 2 the state is D state. When this value is again decreasing, that is L is equal to 2, this L is equal to 2, but this L here resultant NL is equal to 1, and for this 1 the state is P state, and when this L is equal to 2 and this is opposite, that is L is equal to 2, then for this the resultant ML is equal to 2 minus 2 0, and for 0 it is S state, therefore S state. So in this way the d electrons show the configuration with different ML values and their electronic states, that is energy states of different arrangements. So with this we will stop our discussion. Please subscribe to this channel if not yet. Please press the like button and bell icon also. Thank you very much for watching.